Thank you, Jane, for the introduction, and good afternoon, everyone, and good morning and good evening in the other parts of the world. My name is Martin Scheringer, and I will speak about the problem of complexity, probably too much complexity in the chemicals area. I'm a chemist by training. I work as a professor of environmental chemistry at the Masaryk University in Brno in the Czech Republic, and as a senior scientist and group leader at the Swiss Federal Institute of Technology, or ETH, in Zurich in Switzerland. Today, I will not speak about the topic that we often have, which is methods and techniques for the hazard and risk assessment of individual chemicals. That's what we normally are concerned with, how to develop a new method or make an existing method better, or how to understand what the limitations of existing methods are, what kind of data do they generate, and so on. And this is important, and we have made a lot of progress in the discussion and in development of these methods used in regulatory risk assessment of chemicals. But today I will speak about the big picture of, let's call it, all chemicals on the market, which is more difficult and more challenging as a topic. So how big is this big picture, and where can we start this kind of conversation? And perhaps we can just start by looking at the numbers of chemicals on the market. Before REACH entered into force in the EU, there were lists of what was called the existing and the new chemicals, and the vast majority of all chemicals were existing chemicals. They were listed in an inventory called ANEX, and these were about 100,000 substances. And then there were another 5,000 to 6,000 substances, new substances in E-links. But the European market is just one part of the world, and recently Zhanwen Wang and colleagues looked at inventories in other parts of the world overall. They looked at 22 inventories from 19 countries, and they found more than 350,000 chemicals were listed or are listed in these inventories. So it may be that the global market, or the markets, perhaps it's fragmented to some extent, but the global market is much bigger than what we see from the EU. Then REACH came and entered into force in 2007, and as of now, I just checked this morning, under REACH there are now 23,285 substances that have been registered, and there are a bit more than 100,000 dossiers for these substances. So REACH has accomplished one of its goals to remove chemicals from the market that are no longer viable, let's say. But still, the number is quite high, and this may be a problem, And why is this? And we may go back in time, let's say 25 years, to understand why there is a problem. This is a graph from an interesting report by the European Environment Agency, EEA. It was published in 1998. It is available on the internet, you can download it. And it shows a bar chart, or has these columns. And the column here on the left is exactly this number of about 100,000 chemicals, former existing chemicals that were on the market in the EU. And you can already see there is an indication of the problem, because in the larger brown part of that column, it says little or no toxicity data. And then the question is, at the time, it was the government authorities who were responsible for the risk assessment of existing chemicals. And the question is then, how many of these risk assessments had been conducted? This regime was introduced in the 1980s, and this question was asked at the end of the 1990s, so let's say 15, 20 years of time when the government authorities were working on chemical risk assessments. And the number of risk assessments completed in 1997 was 10. Not 10%, but just 10 chemicals. That is shockingly low, and was one of the main reasons why many people agreed that this was not an acceptable situation, and this is also why REACH then was initiated. By introducing REACH, what has been changed, of course, is the roles and responsibilities of the different actors, of industry, of authorities. Also, the regulatory context of all of this has been changed. But what has not been changed is the task as such. It is still the same task of evaluating all these chemicals. And therefore, it is not at all surprising that there are still many problems with missing or incomplete data that would be needed for the assessment of all these chemicals on the market, even if it's a substantially smaller number of chemicals now. Here is a report from Chemical Watch just a week ago where this point is made. It says extensive improvements still needed for REACH, CLP, industry data. ECHA, the European Chemicals Agency, reports that after 14 years of REACH, information provided by industry in their registration dossiers still needs extensive improvement. As I said, I don't find this surprising because the task is still huge and it is a lot of work to conduct a thorough and comprehensive risk assessment of a chemical. And there have been many of these reports over the years that these problems have been there and have persisted. Just earlier this year, in February, also Chemical Watch reported that in the 2020 compliance check, nearly 90% of the dossiers tested or checked needed more data, were not complete. And specifically, it says that what they did in the 2020 compliance check was they looked at 271, or they performed 271 checks for 258 substances and had to request more information in 240 of the checks, which is almost 90%. And what was missing was information on long-term effects on the development of unborn children, on genetic mutations, and on aquatic toxicity. So quite different, but all important endpoints where there was still not enough information provided. So this is the underlying problem of the complexity of the chemical universe or of the substances on the market. This is also something that we see in other parts of the world. Here, and this is a piece of our own work that we conducted a couple of years ago. And here we also included data from the US, from the SmileCast database, and merged them with the European databases. And we arrived at a total of 95,000 chemicals and some basic data for them. And our question in that project was, what are the data that are available for the PBT, the persistence, bioaccumulation, and toxicity assessment of these chemicals? As you can see here in this graph, of these 95,000 chemicals, only a very small fraction, about 3%, had data, measured data, on these three endpoints: acute aquatic toxicity, bioconcentration factor, and biodegradation half-lives, measured half-lives. And this is a graph that was published in the UNEP yearbook in 2013, based on our work by Sebastian Stempel in our group in Zurich. So we see this problem of many chemicals that have not been fully characterized and for which it has not been understood what they may actually do or not do in terms of harm. But these chemicals are not just in lists, they're not just listed somewhere in inventories, they are also real. They circulate in the environment, they also reach the human body. And here is a recent and I think impressive and important human biomonitoring study that shows how many chemicals are present in the human body where they should not be. There are many, there are hundreds and thousands of human biomonitoring studies that demonstrate the presence of chemicals in human tissue, but this one is a particularly comprehensive and thorough recent study. What they did is the authors looked at 30 pairs of mothers and their newborns in the city of San Francisco, and they screened for many chemicals in the maternal blood and the cord blood of these pairs of mothers and newborns. And they found a wide range of chemicals, including 55 chemicals that had never been reported before. So it was that was a really new finding to see them in people. And of these 55, 42 are of unknown origin. It was not clear at all where they come from and why they were in the body of these people. And I think that is also very important to see. It's not that a mother was, for example, exposed to some chemical which it was clear that she used it, be it in her work or at home from a certain product. No, it was really chemicals that come from somewhere, nobody really knows where they come from. So that is about chemicals in human tissue, but they are also present, chemicals are also present in materials where we don't want to have them. And that's also what Martin mentioned before in the first talk this afternoon. This is non-intentionally added substances that are present in plastics. So in addition to all the chemicals that are made and used intentionally. And in this slide, you see 2 chromatograms of extracts from a piece of meat and the package from which or where this meat was stored, and or is the cover of the package. The package was made of polyethylene, and the cover also contained some glue by which it was connected with the main part of the package. And these extracts show now the chemicals that were found in both the or that came out of the cover, and chemicals that then also were present in the meat. And you see then that this is kind of a mirror image, or that is a connection here that indicates the migration of these chemicals from the plastic, from the polyethylene, to the meat. There are 2 groups of substances here. The POSH are the polyolefin oligomeric saturated hydrocarbons, and they are from the polyethylene. And the MOSH, the mineral oil saturated hydrocarbons, are from the glue. And our concern here is not just that they are present in the polymer, in the plastic, but also present in the meat, in the food that people eat, because normally we would assume a plastic package should be safe and clean, and we would not expect as consumers that these chemicals are present in our food. So what can we do in this situation? And I think we have to come to the conclusion somehow, after now 4 or 5 or more decades of hard work on chemicals assessment, regulatory chemicals assessment, we have to come to the conclusion that we need to reduce the complexity of the portfolio of chemicals on the market, and also need to reduce the chemical complexity of materials. I think that is something we have to face as a perspective. Where would we start with this? Of course, we would not start just somewhere. We would start where the chemicals, with the chemicals that are most important in terms of hazards and concerns. And these are, for example, in the EU, substances of very high concern. Just one example, this is PFAS, per and polyfluoroalkyl substances. And as you may have heard, there are many of these substances in use in many different applications. This is a paper by a team, the Global PFAS Science Panel, where I am a member. We published this paper last year. We identified 200 uses of more than 1,400 individual PFAS. And then the question, of course, is which ones of these can be removed? Which of these uses should be removed with the highest priority? And to answer this question, we used what's called the essential use concept. So that's another paper. It looks very similar, but it's another paper from the same team, the Global PFAS Science Panel. And we use this concept of essential use to identify which uses of PFAS would be non-essential and may be removed. And these are primarily uses in consumer items, such as carpets, dental floss, ski wax, climbing ropes, baking paper, bicycle lubricants, skin cream, household cleaning agent, and many more. And in these cases, it could be demonstrated that there are alternatives available that make it possible to have all these products with basically the same performance without PFAS. So that's just an example of how this could be done to make a start on this task, of this daunting task of understanding this complexity and also then trying to reduce it in a systematic way. So in conclusion, I think we have to draw this conclusion that many chemicals are not under control. Many chemicals that we want to use, that we put on the market, are not under control. They are only poorly characterized, or even worse, the properties are unknown. They are found in human bodies, and they are found in materials of also many consumer items, daily use items of people, in food and water. And of course, they make recycling difficult because they would then be present in materials where they should not be there. So it's only downcycling that will be possible in the end, as long as we have so many chemicals in the wrong place, present in the wrong place. So I think after many decades of chemical research and material science research that has led to an increasing chemical sophistication and to a lot of insight and knowledge about materials, it is now time to change the direction of research and development and see chemical simplification as the goal of innovation. So this is not meant to go back, but to go forwards. And because it's not trivial, not obvious how we should make materials that are technically good, have a good performance, and still are simpler and than what we have right now. And I think this thinking along these lines would also help to put the chemical strategy for sustainability into practice. Thank you for your attention.